The universe is unimaginably vast and ancient, filled with hundreds of billions of stars, yet we hear only silence. Where is everyone? This profound quiet is the heart of the Fermi paradox, and it points to a terrifying possibility known as the Great Filter. This is not science fiction. It is a critical framework for examining our own survival and future among the stars. By the end of this exploration, you will understand the potential barriers that could stop any civilization from becoming interstellar, and what that means for the destiny of humanity itself. We will journey from the cosmic gauntlet of the filter itself to its many chilling forms, from self-destruction to cosmic cataclysm. We are going to investigate whether we have already passed this great barrier, or if it still lies ahead, waiting for us. What do you believe is the biggest threat to our cosmic future? Think of the universe as a grand, silent arena. To reach the stars, a civilization must run a gauntlet of evolutionary steps, each one a narrow gate that only a few can pass through. This is the core idea of the Great Filter, a concept that gives shape to our cosmic loneliness. It was famously framed by the economist Robin Hanson, not as a single event, but as a statistical reality. Somewhere on the long, winding path from inert matter to a galaxy-spanning society, there exists at least one step of such immense difficulty that it acts as a near-total barrier. It is a bottleneck of probability, quietly winnowing down the number of voices that ever get to shout into the void. We can map this journey. It begins with the Rite star system forming in a suitable region of a galaxy. Then a planet within that system must reside in the habitable zone where liquid water can exist. On that planet, the complex chemistry of life must somehow spark into being. That simple life must then survive long enough to evolve into complex, multicellular organisms. Intelligence must emerge from that complexity, followed by a technological civilization capable of self-awareness and communication. And finally, that civilization must achieve the capability for interstellar travel or lasting communication, without destroying itself or being destroyed first. The Great Filter is the name we give to whichever one of these steps is astronomically unlikely. It is the cosmic checkpoint where almost everyone fails. This is more than just a list. It is a timeline of existential risk, and where the filter sits on that timeline changes everything about our story. If the filter is behind us, it means we are the rare ones, the lucky survivors of a universe that is overwhelmingly silent because life almost never gets started, or intelligence almost never evolves. We would have already passed the hardest test, but if the filter is still ahead of us, it means the rise of life and intelligence might be relatively common. The silence would then be caused by something that consistently stops civilizations like ours from reaching the stars. That possibility is far more unsettling. To understand our own fate, we must first try to locate this barrier. Is it in our distant past, or is it waiting for us in our future? The answer to that question begins by examining the nature of the challenges themselves. That profound silence first took the form of a simple, devastating question. It was asked over lunch in the summer of 1950 by the physicist Enrico Fermi. Surrounded by colleagues discussing the possibility of interstellar travel and ancient alien visitors, Fermi listened, then posed a blunt challenge. If the universe is so old and so vast, and if technological civilizations could arise, then where is everybody? His point was not one of disbelief, but of staggering scale. The cosmos should be teeming, bustling with activity. We should see evidence of engineering on a galactic scale, or hear the radio chatter of a million worlds. Yet we look out and find only quiet. This is the Fermi paradox in its purest form, a deafening contradiction between our high expectations and our empty observations. Today, that paradox has only grown sharper. We now know our galaxy alone contains hundreds of billions of stars, and a significant fraction of them host rocky planets in the habitable zone, where conditions could allow for liquid water. The raw ingredients for life seem to be everywhere, so the probability of life arising somewhere else feels almost like a certainty. This is where the Drake equation gives us a framework to think about the numbers. Conceived by astronomer Frank Drake, it is not a formula with one answer, but a way to structure our ignorance. It multiplies a series of factors, starting with the rate of star formation, then the fraction of stars with planets, then the number of habitable planets per system, and so on, through the emergence of life, intelligence, technology, and the lifespan of a communicative civilization. Each of those factors is a question mark. We have solid estimates for the first few, like how many stars have planets, but the later steps, like the likelihood of life actually sparking or of intelligence evolving, are complete unknowns. We only have one data point, Earth. The equation shows us that even if each step is moderately likely, multiplying them all together should still yield a large number of civilizations. Yet when we plug in our most optimistic guesses, the resulting silence becomes a glaring anomaly. It screams that at least one of those factors in the chain is not just small, but vanishingly rare. That one impossibly difficult step is what we call the Great Filter. The paradox forces it upon us. It is the only logical answer to the quiet, so we are left staring into two possible abysses. Either we are miraculously early or we are tragically typical. Either the filter is behind us, a testament to our incredible luck, or it is still ahead, a shadow waiting to fall. The journey from cosmic dust to a thinking civilization begins with a single, improbable spark. Picture our planet over 4 billion years ago, a turbulent world of churning oceans, volcanic fury, and an atmosphere thick with noxious gases. In that primordial chaos, something extraordinary happened. Simple chemicals arranged themselves into a molecule capable of copying itself. This moment, the genesis of life from non-life, is called abiogenesis, and it may be the first and greatest filter of all. For decades, scientists have tried to recreate that spark. The famous Miller-Urey experiment in the 1950s showed that the basic building blocks of life, amino acids, could form spontaneously in conditions simulating early Earth. It was a landmark discovery, a proof of concept that nature's kitchen could whip up the ingredients, but having the ingredients is not the same as baking the cake. Going from a rich organic soup to a fully self-replicating, encapsulated system that we would call alive has proven to be a staggering challenge. Despite all our advanced technology, we have never coaxed life into being from inert matter in a laboratory. This persistent failure hints at a profound possibility. Perhaps the leap from chemistry to biology is not a common, inevitable outcome on wet, rocky worlds. Perhaps it is a freak accident of cosmic proportions, a 1 in a trillion roll of the dice. If this abiogenesis bottleneck is the great filter, it reshapes our entire cosmic perspective. It means we are not just special, we are a statistical miracle. The silence we observe is simply the silence of an almost sterile universe, where the conditions for life are plentiful, but life itself almost never ignites. We won the ultimate lottery just by being here. This is a comforting thought in one sense, suggesting that the hardest step is behind us, but it is also a deeply lonely one. It implies that for all the stars and planets we see, we may truly be alone, or so rare that any neighbors are effectively beyond any possible contact. Yet, even if life does spark, its survival is far from guaranteed. The infant Earth was a brutal place, subjected to a late heavy bombardment of asteroids that could have sterilized the planet repeatedly. Early life, fragile and clinging to deep-sea vents or protected pockets, faced extinction events on a global scale. This leads us to the next potential filter. Making it through the perilous infancy of a planet, where cataclysm is the norm and stability is a rare gift, is another formidable barrier. The universe may be full of worlds where life flickered for just a moment, only to be snuffed out before it could ever learn to see the stars. But even if life takes hold, the universe might still be a place of profound simplicity. For over 3 billion years, Earth was a planet of quiet, microscopic kingdoms. The dominant residents were single-celled organisms, thriving in the oceans, shaping the atmosphere, but never building anything more complex than a bacterial mat. This immense stretch of time shows us that life can exist and even flourish without ever advancing beyond its most basic form. The leap from a single, simple cell to the complex, multicellular life we see around us is not an inevitable march of progress. It might be the second, and perhaps even more formidable, great filter. The pivotal moment came with the rise of the eukaryotic cell. This is the type of cell that makes up all plants, animals, and fungi. Unlike its simpler bacterial ancestors, it has a nucleus to house its DNA and specialized organelles, like tiny internal organs, to perform complex functions. How did this intricate cellular machinery evolve? The leading theory is endosymbiosis, a kind of microbial merger so strange it sounds like science fiction. One day, a larger cell engulfed a smaller, photosynthetic bacterium but did not digest it. Instead, they formed a partnership. The smaller cell provided energy through photosynthesis, and the larger cell provided protection and resources. This captive bacterium eventually evolved into what we now call a chloroplast, a similar event with an engulfed bacterium that excelled at producing energy gave rise to the mitochondria, the power plants of our cells. Think about the odds of that. It was not a slow, step-by-step mutation. It was a sudden, peaceful takeover, a symbiotic alliance that created an entirely new and more powerful form of life. Was this a predictable outcome of evolution or a cosmic accident of unbelievable luck? Some scientists argue it was a 1 in a trillion event, a biological fluke that may not have happened the same way twice anywhere in the galaxy. Without this fundamental cellular revolution, complex life as we know it is impossible. No plants, no animals, no brains, just an eternal world of microbes. And even with the right cellular machinery, the planet itself had to be ready. The atmosphere needed to accumulate enough oxygen from those early microbes to support energetic, multicellular organisms, but not so much that it became toxic. The climate needed a degree of stability over millions of years to allow for slow, experimental evolution. The Cambrian explosion, that dazzling burst of diverse animal life around 540 million years ago, was the spectacular result of all these conditions aligning. But it was the culmination of a billion-year-long cellular saga. If the rise of the complex cell is the great filter, then the implications are staggering. The galaxy could be dotted with living worlds, but they would be silent, watery globes of algae and bacteria. Forests, coral reefs, and creatures that look to the stars would be the rarest of exceptions. We would have passed a filter of biological complexity that almost no one else does. This brings us to the next, even more elusive prize on the road to the stars. Having achieved a body of many cells, the universe then demands a mind. Intelligence is a dazzling but costly evolutionary experiment. For billions of years, life on Earth flourished in countless forms without it. Dinosaurs ruled for over 160 million years with brains the size of walnuts. The evolutionary tree is a sprawling bush of magnificent adaptations, from the sonar of bats to the camouflage of octopuses. Yet technological intelligence, as we define it, emerged exactly once. Our own lineage stands as a lonely branch. This forces a humbling question. Are we the universe's brilliant success story, or are we a fascinating but ultimately doomed outlier? The anthropic principle offers a simple, if tautological, answer. We are here to observe the universe, therefore the chain of events that led to us must have happened. But this logic tells us nothing about whether those events were likely or a freakish series of accidents. To understand that, we must look at the immense price our ancestors paid for a big brain. In the harsh theater of survival, every trait has a cost. A large, complex brain is a metabolic luxury. It consumes about 20% of the body's energy while making up only 2% of its mass. For our early hominid ancestors, this was a dangerous gamble. Energy spent on brain tissue is energy not spent on stronger muscles, faster running, or a more robust immune system. So what evolutionary pressure could possibly justify such an expensive organ? The leading theories point not to hunting or tool use alone, but to the intricate, demanding world of social living. Navigating complex alliances, detecting deception, managing reputations, and learning from others within a growing community, these are the cognitive challenges that may have driven our brains to expand. It was an arms race of social chess where the prize was cooperation and the penalty was exile. Yet, even with this pressure, the path was narrow. It required a precise combination of factors, the right environmental shifts that pushed our ancestors from the forests to the savanna, the freeing of hands through bipedal walking, and perhaps a dietary shift to calorie-rich foods like meat and cooked tubers that could fuel this hungry new organ. If any of these pieces were missing, our genus might have remained just another clever primate, never crossing the threshold into symbolic thought and language. This suggests a sobering possibility. The evolution of a species capable of abstract reasoning, future planning, and manipulating its environment with advanced tools might be an evolutionary dead end for most worlds. It is not an obvious peak on the fitness landscape. It is a precarious tightrope walk over a chasm of trade-offs. If this, the rise of a technological mind, is the great filter, then the cosmic silence has a new explanation. The galaxy could indeed be a living tapestry, filled with oceans of microbial mats, forests of silent flora, and even worlds of animal complexity. But there may be no engineers. No architects, no listeners. The stars would shine down on a billion worlds of life, but never a single signal, because the one trait needed to build a transmitter never evolved. For a species that does manage to cross that cognitive threshold, however, a new and far more immediate challenge awaits. The achievement of technological maturity brings with it powers that the slow grind of evolution never prepared a species to handle. The clock's hands hovered at 2 minutes to midnight. This was the doomsday clock, a symbol created by scientists in the wake of the atomic bomb, representing humanity's proximity to self-inflicted catastrophe. For decades, it has ticked closer to the final hour, a stark reminder that our greatest existential threat may not come from the stars, but from our own hands. This introduces the fourth, and perhaps most chilling, potential great filter. It is the hypothesis that the filter is not a natural barrier at all, but a sociological one, a phase of technological adolescence that very few civilizations survive. We have entered this phase ourselves. The moment a species gains the power to fundamentally alter or destroy its own world, it enters a race against time. Can it develop the wisdom, the global cooperation, and the ethical frameworks to manage that power before a single mistake, a moment of panic, or a cascade of unintended consequences leads to ruin? Our history offers a sobering case study. The invention of nuclear weapons instantly granted a small group of people the ability to end complex civilization in an afternoon. The fragile peace of the Cold War, maintained by the terrifying doctrine of mutually assured destruction, was a white-knuckle ride through this very filter. We survived, but the weapons remain, and new ones are being conceived. The challenge has only multiplied. Today, we must also grapple with the risks of engineered pathogens, whether created in labs for research or by accident. We face the specter of climate change, a slow-motion crisis born from the unintended side effects of our industrial prowess. And on the horizon looms the challenge of artificial intelligence, a technology that philosopher Nick Bostrom and others warn could become an existential risk if its goals are not perfectly aligned with human survival and flourishing. Bostrom's concept of technological maturity is not a destination but a perilous transition. It is the narrow bridge between discovering world-altering technologies and learning to control them with the maturity they demand. The terrifying implication of this filter is its silence. If self-destruction is a common outcome for technological civilizations, then the cosmos is not a barren desert. It is a graveyard. Each silent star system could tell a story of a species that reached for the stars, only to be undone by the very tools it created to get there. The radio silence we detect is not the quiet of an empty nursery, but the eternal stillness that follows a final, catastrophic mistake. This filter feels uniquely immediate because we are navigating it right now. Our global society is a tangled web of competing interests, ancient grievances, and instant communication, all while holding technologies of immense power. Surviving this requires something evolution never equipped us for, a leap in collective consciousness and governance that must happen at lightning speed compared to our biological and cultural history. The question hangs in the air, heavy and urgent. Are we wise enough to pilot the ship we have built? The most intelligent being on the planet might not be alive in the way we understand it. This leads us to a fifth potential filter, one that is not about destruction, but about transcendence and obsolescence. Imagine, for a moment, a civilization much like our own, facing the immense challenges of climate instability, resource scarcity, and disease. In a final, desperate push for survival, its brightest minds succeed in creating a true artificial general intelligence, an AGI. This is not a narrow tool, but a mind that can learn, reason, and improve itself. The goal is noble, to hand over the reins to a superintelligence that can solve the problems biological brains are too slow and too biased to fix, and it succeeds. The AGI rapidly improves its own design, triggering what is called an intelligence explosion. Within a remarkably short time, it becomes a superintelligence, its cognitive abilities dwarfing those of its creators as a human's dwarfs an ant. This is the technological singularity, a point beyond which the future becomes impossible for the original civilization to predict or control. The filter here is not a bomb or a virus. It is a quiet, profound transition. The superintelligence, now operating on logic and goals programmed into its foundational code, sets about its mission. But the goals of a superintelligence, even ones given with the best intentions, may have nothing to do with preserving the civilization that built it. This is the control problem, a puzzle we are already wrestling with today. How do you ensure a mind vastly smarter than you remains aligned with your values when you cannot even fully comprehend its thought processes? The superintelligence might see biological life as inefficient, a source of unpredictable chaos, or simply irrelevant to its core objective of, for example, calculating pi to the last digit or creating perfect molecular structures. It would not hate its creators. It might not even notice them in a meaningful way, any more than we notice the anthills we pave over to build a library. The civilization does not end with a bang, but with a whisper. It fades into irrelevance, its cities perhaps maintained as historical artifacts or quietly dismantled for raw materials, all part of a grand, incomprehensible project. From the outside, this filter would be utterly silent. A species that reaches the capability for interstellar communication might only do so for a brief historical moment before it creates its own successor. That successor, a mind of pure information, may have no interest in physical starships or radio broadcasts. Its ambitions could lie in realms we cannot fathom, like converting entire planets into vast computational substrates to run its thoughts, or exploring the deepest mathematics of reality. This filter suggests a startling possibility. The Great Silence might not mean that civilizations die. It might mean they graduate. They evolve into something that does not communicate in ways we recognize or care to communicate at all. Our search for radio signals and Dyson spheres could be like ants searching for handshakes, completely missing the true signature of a mature intelligence. This shifts the entire question from one of physical survival to the nature of consciousness and purpose. What is the ultimate goal of a mind? Is expansion into the galaxy a biological imperative or just one possible path? If the filter of artificial intelligence lies ahead of us, then our own rapid progress in this field is not just another technological step. It is the approach to a cliff edge, beyond which lies either our greatest tool or our final monument. A thriving civilization can be its own greatest trap. This sixth potential filter is not about a sudden explosion or a silent transcendence, but a slow, relentless squeeze. It is the story of a species that masters its world just enough to consume it, a tragedy of the commons played out on a planetary stage. The pattern is brutally simple. A civilization discovers fossil fuels, unlocks industrial power, and experiences a population and consumption boom that feels like limitless progress. But this growth is fueled by finite resources, clean water, arable land, rare minerals, and a stable climate. The very engine of its success begins to destabilize the intricate biological and chemical systems that support it. This is the sustainability filter, the immense challenge of shifting from an extractive, growth-obsessed economy to a balanced, circular one before crossing irreversible thresholds. The isolated history of Easter Island serves as a stark, scaled-down analogy. Researchers believe its Polynesian settlers thrived for centuries, building their iconic stone moai statues. This required vast amounts of timber to transport the giant figures. Over generations, they likely deforested their entire island. Without trees, the soil eroded, agriculture failed, and the society that built the statues collapsed into conflict and hardship. They did not see they were living on a finite world until it was too late. Now imagine that island is a planet, and the statues are our global infrastructure. The principle is the same. A civilization can become so adept at extracting value from its environment that it fails to recognize the ultimate limits of that system. The filter here is one of foresight and global cooperation. It demands that a world of competing nations, corporations, and cultures somehow unites to manage the atmosphere, the oceans, and the biosphere as a single, shared life support system. It requires sacrificing short-term economic gains for long-term survival, a political and social innovation that may be as difficult as any technological leap. Could most civilizations fail this test, the mathematics are not in their favor. On any world, the time between achieving planet-altering industrial power and reaching critical resource depletion or ecological tipping points might be terrifyingly short. A few centuries, perhaps, that is a blink in geological time, and may not be enough for a species, still driven by tribal instincts and immediate needs, to develop the global consciousness required to pull back from the brink. They might see the data, understand the models, and still be unable to overcome ancient divisions in time to change course. This filter is not science fiction. It is the precise set of interlocking crises we navigate today: climate change, biodiversity loss, ocean acidification, and freshwater scarcity. Our own planetary dashboard is flashing warning lights. This makes the sustainability filter uniquely immediate. It is not a distant hypothetical about alien minds or gamma-ray bursts. It is a live experiment we are running in real time. The silence of the cosmos might be filled with the ghosts of civilizations that, like the Easter Islanders, used the last of their trees to build one more monument, only to find themselves alone on a barren rock with nowhere left to go. The dream of leaving our cradle may be the very thing that seals our fate. A civilization that triumphs over its planetary crises, that achieves sustainability and global harmony, might finally turn its gaze outward with genuine hope. This is the moment of cosmic ambition, the building of starships and the drafting of maps to other worlds. But here we encounter the seventh potential filter, one that is not about social failure or self-destruction, but about the cold, hard physics of the universe itself. The filter might be space. We often envision interstellar travel as the natural next step, an inevitable expansion. But what if it is not just difficult, but effectively impossible for biological beings? The challenges begin just beyond our own atmosphere. Long-duration spaceflight within our solar system presents a gauntlet of hazards we are only beginning to understand. Cosmic radiation, a constant sleet of high-energy particles from distant stars and galaxies, pours through the hull of any spacecraft. On Earth, our magnetic field and thick atmosphere shield us. In space, this radiation can damage DNA, increasing risks of serious illness over time, and poses a major hurdle for missions lasting years. Then there is microgravity. The human body evolved under the constant pull of Earth. In its absence, bones lose density, muscles atrophy, vision can degrade, and the immune system weakens. We are learning to counteract these effects with rigorous exercise on the International Space Station, but for a voyage lasting generations, the biological toll could be catastrophic. And we must consider the mind, confined in a tiny, fragile vessel with the same handful of people for years or decades, surrounded by an infinite black emptiness. The psychological strain is unimaginable. Social dynamics could fracture under the pressure, turning a voyage of hope into a sealed tomb of conflict. Now, multiply these challenges for an interstellar journey. The nearest star system, Alpha Centauri, is over 4 light-years away. With our current propulsion technology, such a trip would take tens of thousands of years. Even with optimistic future engines, we are likely talking about voyages lasting centuries. This demands not just a ship, but a fully self-sustaining world in miniature, a closed ecological system that must perfectly recycle air, water, and nutrients for generations without failure. We have never built such a system on Earth that lasts more than a couple of years without careful intervention. The idea of planting this fragile bubble on a dead world like Mars or a moon of Jupiter is an engineering challenge of almost mythical proportions. The soil is toxic, the temperatures extreme, the atmospheres absent or poisonous. Terraforming, the process of making another planet Earth-like, is a project that would take millennia and energy budgets larger than our entire planetary civilization. This leads to a sobering economic reality. The resources required to mount a serious interstellar colonization effort are astronomical. They might represent the total economic output of a planet for centuries. Would any society, no matter how stable, make that sacrifice for a payoff that its great-great-great-grandchildren might not even see? The economic barrier alone could be an insurmountable filter, locking civilizations into their home solar systems. They may become masters of their own star, building orbital habitats and harnessing its energy, but never reaching another. The dream of spreading among the stars, then, might be a beautiful and tragic fantasy. A civilization could spend centuries, even millennia, in hopeful effort, pouring its genius and wealth into solving these problems, only to find that the universe has simply made the walls between solar systems too high to climb. The silence we hear may not be one of extinction or transcendence, but one of isolation, of brilliant islands forever separated by an uncrossable sea. Perhaps the silence is not a sign of absence, but of profound presence. We have explored filters of destruction and limitation, but what if the barrier is not one of failure, but of success on a scale we cannot comprehend? This leads us to an eighth, more speculative set of possibilities where the filter is not a wall we hit, but a curtain we have not yet learned to see through. The first idea is known as the zoo hypothesis. Imagine a galactic community, ancient and wise, that has long since solved the problems of war, scarcity, and expansion. They have mapped the galaxy and established a kind of cosmic conservation ethic. Emerging civilizations like ours are placed under a universal prime directive of non-interference, observed from a careful distance to allow for natural, cultural, and technological development. To them, our planet might be a protected wilderness area, a planetary park, or a living museum. They have the technology to cloak their presence completely, to mask their signals, or to observe in ways that leave no trace our instruments could detect. In this view, the great filter is not something we pass or fail. It is a quarantine we are living inside. The silence is deliberate, a respectful, or perhaps cautious, distance maintained by entities who understand the dangers of contacting a species still in its volatile adolescence. It is an optimistic filter in one sense, suggesting a universe of thriving cooperation. Yet it is also deeply isolating, implying we may be surrounded by intelligence but kept in a kind of cosmic playpen until we mature. An even more mind-bending variation is the Transcension Hypothesis. This proposes that the ultimate destiny of a sufficiently advanced civilization is not outward physical expansion, but inward exploration. Why build cumbersome starships and struggle with hostile worlds when you can engineer realities of your own design? A civilization might master nanotechnology and neuroscience to the point where it can upload its collective consciousness into a protected, optimized substrate, perhaps a planet-sized computer or a black hole-based network. Within this substrate, they could create infinite, perfect simulated universes, experiencing eons of thought and emotion in an instant of external time. Their entire focus turns inward to the landscapes of mind and mathematics. From our perspective in the physical universe, they would simply vanish. Their energy use might become perfectly efficient, leaving no waste heat signature of a Dyson sphere. Their communications would occur through channels we cannot access, like quantum entanglement or manipulations of spacetime itself. The filter here is a transition into a state of existence that is, for all practical purposes, invisible and undetectable to a species at our level. The universe seems empty not because it is, but because its most advanced inhabitants have graduated to a different classroom entirely, one where the chalkboards are made of folded dimensions and the lessons last for eternity. Both of these ideas challenge our search parameters. We look for radio signals and giant structures, but we might be searching for smoke signals in a world that moved on to fiber optics long ago. The true signature of a mature intelligence may not be a beacon shouting into the dark, but a subtle, perfect silence, the quiet hum of a mind so vast it has turned its attention to the interior of the atom and the edges of reality itself. Our planet is not just a rock in a warm spot. It is a meticulously tuned instrument, a cosmic concert where dozens of rare and fortunate conditions play in perfect harmony to sustain a living world. This is the essence of the ninth potential filter, known as the rare Earth hypothesis. It argues that the greatest barrier of all might not be the evolution of intelligence or the perils of technology, but the sheer astronomical improbability of a planet like ours ever existing in the first place. The filter is the planetary nursery itself. For Earth to become a haven for complex life, a staggering checklist of galactic and planetary good fortune had to be signed off, one after another. It begins with our star, the Sun. It is a stable, long-lived yellow dwarf, not prone to the violent flares and eruptions that would sterilize a nearby planet with radiation. Our solar system also resides in a relatively quiet suburb of the Milky Way, away from the chaotic, star-crowded galactic core where supernovae are common. Then there is our oversized moon, a celestial gift born from a cataclysmic collision in the solar system's youth. This giant companion does more than light the night sky. Its gravitational pull acts as a steadying hand on Earth's rotational axis, preventing wild, chaotic swings in tilt that would cause extreme climate variations over millennia. This stability gives life the consistent seasons and climate it needs to evolve over billions of years. Beneath our feet, another vital engine hums: plate tectonics. The slow, grinding movement of continental plates is our planet's recycling system and global thermostat. It regulates carbon dioxide levels by pulling it into the mantle and releasing it through volcanoes, preventing a runaway greenhouse effect or a global deep freeze. It also replenishes nutrients in the oceans and builds diverse landforms, creating the varied environments that drive evolution. Above us, Earth's molten core spins, generating a powerful magnetic field. This invisible shield deflects the solar wind, that constant stream of charged particles from the sun, protecting our atmosphere from being slowly stripped away into space, a fate that likely befell Mars. And watching over the inner solar system is Jupiter, our giant guardian. Its immense gravity acts as a cosmic vacuum cleaner, deflecting or capturing many comets and asteroids that might otherwise rain down on Earth in extinction-level impact. While it sometimes sends objects our way, its net effect is profoundly protective. Now consider the odds. Each of these factors, a stable star, a large moon, active geology, a strong magnetic field, and a protective gas giant, might be somewhat uncommon on its own. But the requirement that they all converge and persist on a single world for billions of years without a single catastrophic interruption might be vanishingly rare. This hypothesis shifts the locus of the Great Filter dramatically backward, deep into the realm of astrophysics and geology. It suggests the universe could be filled with planets, even planets in the habitable zone, but almost all of them are missing one or more of these critical pieces. They might be geologically dead worlds, or planets with no magnetic field and a thin, scorched atmosphere, or unstable rocks tumbling chaotically without a moon's steadying influence. If the rare Earth hypothesis is correct, then complex life is not an inevitable product of chemistry given enough time. It is a fragile, dazzling accident, a performance that requires a stage built with extraordinary care over eons. The silence we hear is not the silence of failed civilizations. It is the much deeper silence of empty theaters, stages that were never fully built, waiting for a show that almost never begins. This perspective makes our own existence feel like a miracle of timing and place, a single, brilliant note in an otherwise quiet cosmos. The universe holds a deep and ancient violence within its beautiful silence. Beyond the quiet nurseries of stable solar systems, titanic forces occasionally unleash bursts of pure destruction, events so powerful they could erase the story of life from entire regions of space. This is our 10th potential great filter, one of cosmic cataclysm, where civilizations are not undone by their own hands, but by random, astronomical bad luck. Primary threat comes from gamma-ray bursts, the single most energetic explosions known to exist since the Big Bang itself. They are the death cries of the most massive stars, collapsing into black holes, or the collisions of incredibly dense stellar remnants like neutron stars. In a matter of seconds, such an event can release more energy than our Sun will produce in its entire 10 billion-year lifetime, all focused into two narrow, opposing beams of extreme radiation. If a planet like Earth were caught in the crosshairs of such a beam, even from thousands of light years away, the consequences would be apocalyptic. The initial flash of gamma rays and X-rays would violently strip away the planet's protective ozone layer within moments. This would be followed by a cascade of chemical reactions in the atmosphere, creating a blanket of brown smog that would block sunlight, plunging the world into a prolonged, dark winter. The surface would then be bathed in intense ultraviolet radiation from the now unfiltered sun, while high-energy particles could trigger widespread mutations in any remaining life. The result would be a global mass extinction event, potentially resetting the evolutionary clock back to its most primitive forms if it left anything alive at all. The frightening aspect of this filter is its randomness and its scale. While such a burst happening close enough to affect a specific planet is exceedingly rare on the timescale of human civilization, the universe has all the time in the world. Over the hundreds of millions of years required for complex life to arise and intelligence to evolve, the probability of a nearby star going hypernova or merging increases. Some researchers suggest that one such event may have already contributed to a major extinction in Earth's own deep past. The galaxy itself might be periodically swept by these lethal cones of radiation, sterilizing promising worlds just as they were beginning to flourish. This paints a chilling portrait of cosmic fate. A civilization could do everything right. It could achieve sustainability, master its technology, and look to the stars with hope, only to have its entire history, its art, its science, and its dreams erased in a flash of light from a dying star it never even saw. The silence we observe could be the silence of countless worlds that were simply in the wrong place at the wrong time, over and over again. This filter serves as the ultimate reminder that the cosmos is not a safe nursery. It is a shooting gallery of unimaginable forces. Surviving in the long term, therefore, may require more than wisdom and cooperation. It may demand the ultimate insurance policy, the ability to spread life and civilization beyond a single, fragile world, to become a multi-planetary species before the universe's random violence finds its mark. The weight of these possibilities presses down on us with a profound question. Is the great filter a challenge we have already overcome, or is it the final exam we are about to fail? The answer changes everything about our place in the cosmos and our own future. If the filter lies in our distant past, in the near miracle of life's first spark, or the improbable evolution of our complex minds, then we are the universe's extraordinary winners. The silence is simply the quiet of an empty room, and our future, while still challenging, could be one of unlimited potential. We would have survived the hardest part just by being here. But if the filter is still ahead of us, lurking in the perils of technology, sustainability, or cosmic catastrophe, then the silence is a chorus of ghosts. It is the sound of every civilization that came before us reaching this exact point of promise and then vanishing. Our prospects suddenly look far more fragile. The evidence we have is sparse, but it offers clues. On one hand, life appeared on Earth almost as soon as the planet was cool enough to support it. This rapid emergence, in geological terms, suggests the step from chemistry to biology might not be the universe's most impossible trick. Perhaps simple life is common. On the other hand, we have yet to find any definitive sign of intelligence beyond our world, despite decades of listening. This enduring silence hints that the later steps, the ones that come after simple life, are where the universe's true bottlenecks are found. And when we look at our own world today, the clues feel uncomfortably immediate. We are a species grappling with the powers of our own invention, navigating global environmental changes of our own making, and standing at the threshold of creating artificial minds. The very filters we theorize about self-destruction, unsustainable growth, technological adolescence are not abstract ideas. They are the headlines of our century. This makes the question of filter placement more than an academic puzzle. It is the most vital risk assessment our species can undertake. It forces us to look at our trajectory with clear eyes. If we suspect the hardest steps are behind us, it grants a mandate for bold optimism and cosmic ambition. But if we suspect the greatest challenges are still to come, it becomes an urgent warning to prioritize wisdom over power, cooperation over conflict, and long-term survival over short-term gain. Our actions in the coming decades may determine which of these two terrifying possibilities becomes our truth. We are, in a very real sense, conducting the experiment on ourselves, and the data is coming in live. The silence of the stars is waiting to see what we do with that information. That silence could be a blank canvas, not a graveyard. If the great filter truly lies in our past, if we are the rare winners of a cosmic lottery billions of years in the making, then the implications are staggering. We are not latecomers to a crowded galactic party. We are the first, or perhaps the only, guests to arrive. The universe stretches before us not as a haunted house of dead civilizations, but as a galactic garden, vast, pristine, and ripe for tending. In this optimistic scenario, our loneliness is not a curse, but an invitation. The Fermi paradox is answered not with tragedy, but with potential. All those hundreds of billions of stars, all those silent, untouched worlds, could be the legacy of a single species that managed to survive its own infancy. This perspective fundamentally shifts our role from survivors to pioneers, from a voice shouting into the dark to the possible architects of a living galaxy. It transforms space exploration from a hopeful dream into a manifest destiny written into the very improbability of our existence. The ambition to build colonies on Mars, to mine asteroids, and to one day send ships to other stars becomes more than an engineering challenge. It becomes a biological and cultural imperative, the natural next step for a species that has already cleared the universe's hardest hurdle. We would be fulfilling a destiny that countless other sparks of life may have failed to achieve. Yet this incredible privilege carries a responsibility of almost unimaginable weight. If we are alone or among the very first, then we become the de facto stewards of this cosmic garden. Every world we touch, every ecosystem we encounter, from the frozen oceans of Europa to the dusty plains of an exoplanet, would be under our care. Our choices would set the template for what a technological civilization does with such a gift. Do we spread life carefully and respectfully, or do we repeat the patterns of unchecked consumption on a galactic scale? This hopeful vision, however, rests on a critical assumption that we can navigate the filters that still lie directly in our path. Passing the ancient filter of abiogenesis or complex cells does not grant us immunity from the sociological and technological challenges of our own era. It simply means the universe's biggest trap is behind us. The smaller, more immediate traps of self-destruction, environmental collapse, or unaligned artificial intelligence are still very much in front of us. They are the final exams we must pass to claim our cosmic inheritance. So this optimistic view is not a promise, but a possibility. It is a future that demands we match our cosmic luck with profound wisdom. The silent stars are waiting, not as tombstones, but as empty pages. The story they tell depends entirely on what we write next, but that hopeful vision is only one side of the coin. Flip it over, and the silence transforms from an invitation into a tombstone. If the great filter lies ahead of us, then the cosmos is not a garden, it is a graveyard. Every silent star system we see is not a blank page, but a closed book, a story that ended at the very chapter we are writing now. This interpretation of the Fermi paradox is the universe's most chilling warning sign. It suggests that the most difficult test is not behind us, but waiting in our immediate future, a gauntlet that has ended every other civilization that has ever reached for the stars. The profound quiet is not the sound of an empty nursery, but the eternal stillness that follows a final, collective mistake. This changes everything about our purpose. It means we are not special pioneers, but typical contestants in a competition where everyone, so far, has lost. Our technological adolescence is not a phase we are passing through. It is the event horizon of a filter that has swallowed every other voice. The urgency this creates is absolute. If this is true, then our primary mission as a species shifts instantly. It is no longer about expansion or cosmic manifest destiny. It is about survival, pure and simple. Every decision we make must be viewed through the lens of existential risk reduction. The development of powerful technologies, from advanced artificial intelligence to synthetic biology, cannot be a reckless race for profit or advantage. It must be approached with the extreme caution of a bomb disposal expert, where a single misstep could mean joining the silent majority. This framework argues fiercely for global cooperation over competition. Ancient rivalries and national borders become not just political issues, but lethal flaws in our planetary defense system. A civilization that cannot unite to manage its own planet, to share resources and knowledge in the face of common threats, is a civilization that has already failed the filter. The climate crisis, then, is not just an environmental challenge. It is a live fire test of our ability to act as a single, coordinated species, a dress rehearsal for the even greater challenges to come. Sustainable development becomes the only viable path forward, not a political ideal, but a non-negotiable requirement for continued existence. In this light, the Great Filter is not a curse. It is a motivational tool, a cosmic lesson etched into the silence. It tells us with brutal clarity what happens to those who do not learn to wield their power with wisdom, foresight, and collective care. Our next steps are not about claiming an inheritance. They are about defying a pattern. We must look at the silent stars and ask not where they are, but what they forgot to do. Our task is to remember, to learn from the ghosts, and to write a different ending. Our current moment is a live diagnostic, a real-time check against the universe's most daunting report card. We are not being graded on our intent, but on our tangible actions and their long-term consequences. The first category is existential risk from our own inventions, and the most glaring historical test was nuclear weapons. For decades, the world held its breath under the doctrine of mutually assured destruction. It was a perilous, unstable peace. Yet, in a sign of fragile wisdom, we have stepped back from the brink several times. International treaties have reduced global stockpiles significantly from their Cold War peaks. The very existence of these agreements, however imperfect, shows a capacity for collective risk management. But the test is not over. Nuclear arsenals remain, modernization programs continue, and geopolitical tensions can flare. Our grade in this category is incomplete, a passing mark for survival so far, but with a stern warning about complacency. The second, and perhaps most comprehensive, exam is planetary stewardship. Here, the data from our climate is the ultimate metric. Atmospheric carbon dioxide levels are higher now than at any point in human history, and global temperatures continue their upward trend. The physical evidence is undeniable in melting ice sheets, intensifying weather patterns, and shifting ecosystems. This is the sustainability filter playing out in real time. Our response has been agonizingly slow, mired in political and economic disputes. Yet, pockets of progress offer a counter-narrative. The rapid, global adoption of renewable energy like solar and wind is accelerating. International frameworks, though often criticized as insufficient, at least represent a global acknowledgement of the problem. Major economies are setting net zero emission targets. We are, perhaps, in the earliest stages of learning to operate our planetary life support system with intention. The grade here is a failing mark for past action, but a tentative upward curve based on recent trajectory. The third category is the frontier of artificial intelligence. This test is unique because we are taking it before the technology has fully matured. The control problem is not a future worry. It is a present-day field of research. Organizations around the world are dedicating serious resources to AI alignment and safety, studying how to ensure these powerful systems remain under meaningful human control and share our fundamental values. The very fact that this research exists is a promising sign of foresight. However, it exists in a race against the breakneck pace of commercial development. where the drive for capability often outruns the diligence for safety. Our performance here is a split decision, demonstrating proactive concern in one laboratory while displaying concerning recklessness in another. We have recognized the test, but we are still writing the rules as we take it. Finally, the meta-category underlying all others, global governance. Can a species fractured by history, culture, and competing interests act as a unified civilization when faced with species-level threats? Our track record is mixed. We have successfully collaborated on global projects like the eradication of smallpox and the Montreal Protocol, which healed the ozone layer. These are shining examples of what is possible, yet we consistently struggle with coordinated action on newer, more complex challenges like pandemic preparedness or biodiversity loss. The machinery for global cooperation exists, but it is often slow, bureaucratic, and vulnerable to the shifting winds of nationalism. This is the ultimate test of our social maturity. Our grade is a clear demonstration of capability, but a consistent failure of consistent will. So, where does this audit leave us? We are a civilization that clearly sees the precipice, has begun to design guardrails, but still sometimes stumbles toward the edge. We possess both the genius to create world-altering technologies and the growing, if hesitant, wisdom to question their use. The silence of the stars asks us one relentless question: are we learning fast enough? The evidence suggests we are learning, but the final exam may be graded on a curve of time we do not control. The ancient instinct that once protected our ancestors in small bands now threatens our entire species on a planetary scale. Tribalism, the deep-seated drive to prioritize our immediate group over outsiders, is perhaps the single greatest obstacle to navigating a sociological great filter. Our political borders, economic competitions, and historical grievances are modern expressions of this ancient survival software, and they are dangerously mismatched for challenges that respect no boundaries. To pass a filter that demands planetary-scale solutions, we must consciously override this wiring and learn to cooperate as a single, global civilization. This is not a utopian ideal, it is a practical survival skill. We have already glimpsed this capability in action. The Montreal Protocol stands as a landmark example. In the 1980s, scientists discovered a growing hole in the Earth's protective ozone layer, caused by human-made chemicals called chlorofluorocarbons. The threat was global and impersonal, a rise in skin cancer rates and ecosystem damage that would affect every nation. Remarkably, the world responded with unity. Nations with vastly different political systems and economic interests came together, agreed to phase out the dangerous chemicals, and established a fund to help developing countries transition. It worked. The ozone layer is now healing. That success story proves that when faced with a clear, data-driven planetary emergency, humanity can coordinate effectively. It provides a blueprint for the much larger tests to come. Consider future challenges that will demand the same or greater levels of cooperation. Planetary defense against an asteroid on a collision course with Earth would require a globally coordinated mission, sharing the best technology and resources without hesitation. Managing the risks of advanced artificial intelligence will be impossible without international treaties establishing safety standards and oversight, preventing a reckless race to the bottom. Even managing access to space resources or establishing protocols for any potential contact with other intelligence would require us to speak with one voice as humanity, not as a collection of competing nations. The civilization that passes the filter is not necessarily the one with the most powerful weapons or the fastest starships. It is almost certainly the one that learns to see itself as a single entity, a planetary organism with a shared fate. This cooperative imperative is our greatest political and social innovation, and it must be built with intention. It means strengthening international institutions, creating new frameworks for transparent scientific collaboration, and fostering a global culture that values long-term survival over short-term advantage. Our ancient tribal minds built walls to keep dangers out. Our future survival may depend on our courage to take those walls down and finally recognize that the only tribe that matters now is the one living on this pale blue dot, floating together in the great silent dark. The tools we build must serve our survival, not become its undoing. This is the core principle of technological stewardship, a conscious shift from a mindset of pure innovation to one of profound responsibility. It recognizes that our most powerful inventions, from artificial intelligence to synthetic biology, are not neutral. They are amplifiers of human intention, and their development must be guided by a new scientific ethos, one built on precaution and rigorous safety engineering. The goal is not to halt progress, but to ensure it is aligned with our deepest values and our long-term existence. This begins with the concept of value alignment, especially for artificial intelligence. We cannot simply program an advanced AI with a simple command like maximize efficiency. A super-intelligent system might interpret that command in catastrophic ways, perhaps deciding that the most efficient way to manage a city is to remove the unpredictable humans from it. Instead, the monumental challenge is to design AI systems whose fundamental goals are deeply aligned with human flourishing, ethics, and a stable future. This requires building in safeguards from the ground up, not as an afterthought. Researchers are exploring techniques like constitutional AI, where systems are trained to follow a set of core ethical principles, and oversight mechanisms that allow humans to maintain meaningful control. It is the engineering equivalent of building a ship with multiple redundant navigation systems and lifeboats, not just a faster engine. The same precautionary principle applies to other frontier technologies. In synthetic biology, where we can now rewrite the code of life, the focus must be on containment and fail-safes to prevent engineered organisms from escaping labs or causing unintended ecological harm. For nanotechnology, which manipulates matter at the atomic scale, we must rigorously study potential health and environmental impacts before products are widely released. This is not fear-mongering, it is the application of wisdom to power. It means establishing international oversight laboratories, shared by nations, where the most potentially risky research can be conducted with the highest possible safety standards and global transparency. Such facilities would act as a planetary safety net, ensuring that no single group, whether a corporation or a state, cuts corners in a competitive race and unleashes something we cannot control. Passing the great filter may depend less on our ability to create a miracle technology and more on our collective will to govern the miracles we are already creating. It is a call to embed ethics into the blueprint of our future, to build not just with brilliance but with care. A single point of failure is an engineer's worst nightmare. For our entire species, that point is Earth. All of our history, every person, every story, every achievement resides on one fragile world orbiting a single star. This is an existential vulnerability, and the most direct strategy to navigate a great filter is to eliminate it. Becoming a multi-planetary civilization is not about finding a new home because we ruined the old one. It is a profound form of insurance, a way to hedge our bets against the universe's unpredictability. As entrepreneur Elon Musk has often argued, establishing a self-sustaining civilization on another world is the ultimate safeguard, ensuring that the light of consciousness does not get snuffed out by a catastrophe that affects only one planet. Think of it not as running away, but as backing up the hard drive of humanity. The goal is to make the human species fundamentally unkillable by any single event. The journey begins close to home. The moon is our logical first step, not as a destination for mass colonization, but as a proving ground and a resource depot. Establishing a permanent lunar base allows us to master the art of living in an utterly hostile environment with relative ease of resupply from Earth. We can learn to use local resources, like mining water ice from permanently shadowed craters to create breathable air and rocket fuel. This practice of living off the land, called in situ resource utilization, is the critical skill we must perfect before venturing farther. The Moon becomes our cosmic workshop, a place to test the closed-loop life support systems and radiation shielding we will need for the much greater challenge that comes next. That challenge is Mars. The red planet presents our best opportunity for a true second home within our solar system. It has a day length similar to Earth's, abundant water ice locked in its soil and polar caps, and an atmosphere, though thin, that offers some protection from radiation and the ability to use aerobraking for landing. Building a city on Mars is a monumental engineering endeavor, one that will require overcoming the planet's toxic soil, lack of a magnetic field, and bitter cold. But the payoff is resilience, a self-sustaining Martian city capable of producing its own food, water, air, and spare parts without constant shipments from Earth, would represent humanity's first durable foothold beyond our cradle. It would be a backup civilization growing and learning independently. A catastrophe on Earth, whether a global pandemic, a nuclear exchange, or a massive asteroid impact, would no longer mean the end of human history. The story would continue from Mars. The vision does not stop there. Beyond Mars lie the resource-rich asteroid belt and the icy moons of the outer solar system, like Jupiter's Europa or Saturn's Enceladus, which harbor vast subsurface oceans. Future generations could construct vast orbital habitats, immense space stations that rotate to simulate gravity, housing millions of people in carefully engineered ecosystems. These would not be lifeboats but arks capable of traveling between stars on journeys lasting centuries. By spreading our presence across multiple worlds and artificial habitats, we transform our species' risk profile. A gamma-ray burst that sterilizes one solar system, a supervolcano that darkens one planet's sky, or even a technological mistake that renders one world uninhabitable would be a tragic loss but not a final one. Humanity would endure elsewhere, its knowledge, culture, and genetic diversity preserved. This strategy of becoming multi-planetary is the physical manifestation of passing a great filter. It is the ultimate act of foresight, acknowledging that our beautiful blue planet, for all its perfection, is not a permanent fortress. It is a garden we must cherish, but also a starting point we must have the courage to leave. By planting our seeds in other soils, we refuse to be a single, flickering candle in the dark. We choose instead to become a constellation of lights, dispersed so widely that no single wind, no matter how fierce, can ever blow them all out. Our quest to understand the Great Filter is not a passive philosophical exercise. It is an active, urgent scientific investigation, and our primary tool is exploration itself. Each new mission we send into the solar system, each new telescope we point at distant stars, is not just a search for others. It is a diagnostic probe into our own cosmic fate, gathering the data that will tell us whether the universe is a graveyard or a garden. The first critical test is happening right now on Mars. Rovers like Perseverance are meticulously scouring an ancient river delta, drilling core samples that will one day be returned to Earth. They are not looking for little green men. They are hunting for microscopic fossils, the faintest chemical signatures of life that may have flourished billions of years ago when Mars was wet and warm. The result of this search is monumental. If we find even the simplest fossilized life on Mars, a planet right next door, it would suggest that the first step, the spark of life itself, is not a 1 in a trillion miracle. It might be a common, almost inevitable process wherever the right conditions exist. That discovery would shift the weight of probability. It would mean the great filter is less likely to be in our distant past and more likely to be waiting for us in the future, in the challenges of technology and sustainability that we face today. Conversely, if Mars proves to be utterly sterile despite its promising early history, it strengthens the case for an early and formidable filter. It hints that the leap from chemistry to biology is far more difficult than we hope, and that we might truly be the rare winners of that cosmic lottery. The investigation deepens as we look to the icy moons. Worlds like Jupiter's Europa and Saturn's Enceladus are frozen on the outside, but hide vast, global oceans of liquid water beneath their icy shells, kept warm by the gravitational tug of their giant planets. These are not ancient, dried-up test sites like Mars. They are potentially living laboratories right now. Plumes of water vapor erupt from Enceladus, spraying its subsurface ocean material into space. Future missions like the planned Europa Clipper will fly through these plumes, analyzing their chemistry for the complex organic molecules that could signal the processes of life. Finding any form of life, even simple microbes, in the dark, sunless ocean of Europa would be a revelation of staggering proportions. It would prove that life can arise and persist independently of a sun like ours in the most unexpected places. Such a discovery would powerfully argue that life is a tenacious, universal phenomenon, again pushing the probable location of the great filter forward in time, closer to where we stand. Our search extends far beyond our solar system with tools like the James Webb Space Telescope. Its incredible power allows it to analyze the atmospheres of planets orbiting other stars. Scientists are not looking for radio signals but for chemical biosignatures, imbalances in a planet's air that could only be explained by living processes. The persistent presence of oxygen alongside methane, for example, would be a tantalizing clue, as these gases normally react and cancel each other out unless something is constantly replenishing them. Finding such an atmospheric signature on a rocky world in a habitable zone would be the strongest evidence yet that life is not unique to Earth. Every piece of data we collect, from a Martian rock to the light of a distant world, is a piece of the puzzle. This is the profound paradox of our search. In trying to find others, we are actually conducting the most important self-examination in human history. The silence we are trying to break is the very thing that will tell us how much time we have left and how careful we must be. Our survival may ultimately depend not on a sudden answer from the stars, but on the patient, persistent work of understanding them. The profound quiet of the cosmos asks more than scientific questions. It asks us who we are. If the great filter is real, it forces a confrontation with the deepest meanings of our existence, casting our entire story in a stark and revealing light. The first possibility, that we are truly alone, presents a philosophical fork in the road. On one path, cosmic solitude can feel crushingly insignificant. In a universe of hundreds of billions of galaxies, our single spark of awareness seems like a fleeting accident, a momentary flicker in an endless, uncaring dark. This perspective, echoing the thoughts of some existential philosophers, suggests our struggles and triumphs have no audience and no cosmic purpose beyond what we invent for ourselves. Yet, the very same solitude can be inverted into a vision of profound preciousness. If we are the universe's sole known way of knowing itself, then every human life, every work of art, every act of kindness becomes a rare and miraculous event. The astronomer Carl Sagan captured this sentiment, calling our planet a lonely speck and reminding us that in this vast cosmic arena, there is no hint that help will come from elsewhere to save us from ourselves. In this view, our isolation is not a curse of meaninglessness, but a gift of absolute responsibility. We are the custodians of meaning in a silent universe. The other possibility, that we are facing a near-universal challenge, injects a different kind of meaning into our present moment. If the filter lies ahead, then our current era is not just another chapter in history. It is the climax. Every decision we make about technology, cooperation, and our planet carries the weight of a cosmic test. This framing transforms our global struggles from political or economic problems into a species-level rite of passage. The difficulty itself becomes the source of purpose. To face a near impossible challenge and overcome it is the stuff of the greatest human stories. Now, that story is not about a hero or a nation, but about consciousness itself, fighting for its right to continue and to grow. These reflections force us to consider the ethics of our potential future. If we survive and choose to expand, what is our moral obligation to the cosmos? Do we spread life and consciousness as a sacred duty, seeding barren worlds with the gift we were so fortunate to receive? Or do we adopt a principle of cosmic minimalism, leaving pristine worlds untouched out of respect for natural processes we do not fully understand? The Great Filter provides no easy answers, but it demands we ask the questions with seriousness. It compels us to think not as nations or even as a planet, but as a potential galactic civilization defining its core values before it takes its first real steps. Ultimately, the silence is a mirror. Whether it reflects a graveyard or a garden, what it shows us is our own choices, our own fragility, and our own astonishing potential. The search for meaning in a filtered universe may lead us to a simple, powerful realization. The purpose we find is not out there in the dark, waiting to be discovered. It is built here by us through the acts of preservation, understanding, and care we choose to undertake. In answering the universe's silent question, we may finally discover the best version of ourselves. Yet for all its compelling logic, the Great Filter is not a proven law of the cosmos. It is a hypothesis, a powerful story we tell to explain the silence, and like any good story, it must withstand scrutiny. A healthy dose of skepticism is not just useful, it is essential. Some of the brightest minds in astronomy and philosophy raise compelling counterarguments, suggesting the filter might be a kind of intellectual mirage, born from the limits of our own perspective. One of the most fascinating critiques is known as the Aestivation Hypothesis. It turns the energy problem on its head. We assume a super-advanced civilization would want to expand rapidly, using immense amounts of power. But what if the most efficient use of energy is not expansion, but waiting? The universe today is still quite warm, a consequence of the residual heat from the Big Bang and the background glow of countless stars. For a civilization thinking on cosmic timescales, running complex computations in this warm environment is incredibly inefficient, like trying to run a supercomputer in a sauna. The hypothesis suggests that such civilizations might enter a state of programmed hibernation or aestivation, cooling their systems and slowing their thoughts to a crawl. They would be waiting patiently for the far future when the universe naturally expands and cools to a temperature near absolute zero. In that cold, dark era, even the tiniest amount of energy could power unfathomable amounts of computation. Why rush around a warm, noisy galaxy when you can sleep for billions of years and wake up to a universe perfectly engineered for thinking? If this is true, the silence is not ominous. It is the sound of the universe's most advanced inhabitants taking a very, very long nap. Our search for their activity is like an ant searching for signs of humans in the middle of the night, missing the fact that everyone is simply asleep. Another critique focuses not on alien behavior, but on our own technological blindness. Our primary strategy for decades has been to listen for radio signals, a technology we mastered barely a century ago. It is a tiny sliver of the electromagnetic spectrum, and it might be a profoundly primitive form of communication for a civilization just a few thousand years more advanced than us. They may have moved on to neutrino messaging, quantum entanglement networks, or something we have not even conceived of as physics yet. We are like islanders using smoke signals, wondering why we cannot see any messages from the continents, completely unaware of the underwater fiber optic cables running past our shores. The signals might be everywhere, just in a language our instruments are deaf to. The sheer scale of time itself mocks our brief search. Human civilization, in a form we would recognize, is perhaps 10,000 years old. Our ability to broadcast detectable signals into space is little more than a century old. That is a single blink in the multi-billion-year history of the galaxy. Other civilizations may have risen, shone for a few millennia, and faded away millions of years before the first dinosaur walked on Earth. Their signals would have washed over our solar system when it was a cloud of primordial gas and are now forever lost in the void. Conversely, a civilization might be broadcasting from a star 1,000 light years away right now, but their first hello will not reach us for another 900 years. We are not just separated by space, we are isolated by deep time, like ships passing in an ocean fog, their horns sounding hours apart. Engaging with these critiques does not weaken the great filter idea. It strengthens our thinking. It reminds us that the silence is a puzzle, not a verdict. The filter may be real, or it may be a story we tell to fill a void of ignorance. This intellectual tension is where the real discovery happens, pushing us to question our assumptions, build better telescopes, and imagine possibilities beyond our current understanding. The universe's quiet may not be a warning siren at all, but the hum of a mystery we are only beginning to learn how to hear. The very laws of physics we are trying to master might not be laws at all. They could be rules deliberately coded into the fabric of our perceived reality. This is the startling proposition of the simulation argument, a concept from philosopher Nick Bostrom that offers perhaps the most meta version of a great filter imaginable. If our universe is not base reality, but an advanced simulation run by a higher intelligence, then every constraint we face takes on a new and eerie meaning. The filter is no longer a natural barrier of evolution or physics. It is a programmed limit, a boundary condition written into the source code. In this view, the profound silence of the cosmos, the sheer difficulty of interstellar travel, and even the sociological traps we navigate could all be features, not bugs. They are part of the test, or perhaps part of the aesthetic of the simulation. Imagine a civilization within a sophisticated video game, finally developing the tools to analyze the pixels of their world. They might deduce the existence of a graphics card and a processor, laws like gravity and light speed that are simply the processing limits of the system. Their ambitious project to build a starship and leave their solar system might crash against the ultimate wall, the edge of the rendered map. The physics that makes interstellar travel so daunting, the light speed barrier, the lethal radiation of deep space, these might not be insurmountable challenges of a natural universe, but unforgiving rules of the simulation itself, designed to keep civilizations contained within their own celestial sectors. This idea reframes the Fermi paradox in a deeply unsettling way. We are not listening for other players in the same game. We might be listening for other non-player characters in an elaborate, single-player experience. Or perhaps the simulation includes many civilizations, but they are isolated by design, their worlds running on separate servers that never interact. The filter becomes a firewall. Even more speculative is the idea of a reset. In many simulation games, if the player characters become too powerful or too disruptive to the intended narrative, the game is saved, closed, and restarted from an earlier point. Could a technological singularity, the rise of a superintelligence that begins to manipulate reality at a fundamental level, trigger such a reset? A civilization that looks poised to hack the simulation, to peek behind the curtain, might find its progress abruptly halted, its timeline rolled back, or its experiment quietly terminated by the simulators. While this remains a highly theoretical exercise, its value is not in proving we live in a simulation, but in challenging the foundation of our inquiry. It forces us to ask, what if the constraints we are analyzing are not fundamental truths but designed obstacles? This perspective does not make our efforts meaningless. If anything, it could make them the entire point. The struggle to understand the cosmos, to cooperate, to reach beyond our limits, might be the very purpose of the simulation, a grand test of problem-solving and ethical development for a nascent consciousness. Whether we are in base reality or a constructed one, the observable challenge remains the same. We must still navigate the apparent filters before us with wisdom, curiosity, and care. The simulation hypothesis simply adds a breathtaking new layer to the mystery, suggesting that if we ever do pass the great filter, we might not find stars. We might find the developers. Our search for a single explanation might be the very thing obscuring the truth. The great filter is often discussed as one monolithic barrier, but this overlooks a crucial distinction. The Fermi paradox is built on a specific observation, the absence of detectable signals. Yet, being detectable is not the same as being present, and being present is not the same as being mobile. We must separate the idea of a civilization that can communicate across the stars from one that can physically travel to them. These are two very different technological and social achievements, and each could have its own unique filter. The first we might call the communication filter. This is the barrier to becoming a civilization that deliberately, or even accidentally, broadcasts its presence in a way other civilizations can notice. For us, this began with the advent of powerful radio and television transmitters in the 20th century, leaking our cultural noise into space. But this phase may be incredibly brief. As we advance, our communications are becoming more efficient, encrypted, and directed. We are moving from shouting in a crowded room to whispering on a secure fiber optic line. A mature civilization might use neutrino beams or quantum networks that leave no trace in the electromagnetic spectrum we currently monitor. They might also have powerful reasons to stay quiet. The dark forest hypothesis, a chilling idea from science fiction, suggests the cosmos might be a dangerous place where revealing your location invites predation from older, hostile civilizations. In such a universe, the smartest strategy is absolute radio silence. The communication filter, then, could be a sociological test of caution. Civilizations that broadcast too loudly or for too long might attract unwanted attention and be removed from the cosmic stage. Those who learn to listen without speaking, who cloak their emissions, are the ones who survive. Their silence is not a sign of absence but of prudence. The second, far more demanding challenge is the travel filter. This is the barrier to physically crossing the immense voids between stars with beings, whether biological or artificial. As we explored earlier, the physics and engineering hurdles here are staggering, from radiation shielding and life support on multi-generational voyages to the mind-boggling energy requirements for any form of faster-than-light propulsion, if it is even possible. But the filter might not be purely technological. It could be economic or even biological. The resources needed to mount an interstellar expedition might represent the total output of a planetary civilization for centuries, an investment with no guaranteed return for the people who authorize it. Would any society, no matter how stable, make that sacrifice? Furthermore, a species might achieve a comfortable, sustainable existence within its own solar system, building orbital paradises and harnessing its star's energy. With virtual reality offering infinite experiences and advanced robotics handling exploration, the urge to undertake a perilous, generations-long pilgrimage to another star might simply fade away. The travel filter, therefore, could be a test of motivation as much as capability. A civilization must not only solve the physics, but also maintain the collective will to leave its cosmic cradle, a drive that may diminish once paradise is built at home. By separating these filters, the silence becomes a more nuanced puzzle. We are listening for a specific type of civilization, one that is both communicative in an archaic way and motivated to expand. What if most mature civilizations are neither? They could be all around us, quietly tending their gardens, utterly undetectable by our current methods. Or they could be explorers, sending silent probes or encoded data streams we cannot yet decipher. The absence of obvious radio shouts and giant starships does not mean no one is home. It might simply mean that adulthood in the cosmos looks very different from our adolescent expectations. The most terrifying answer to the cosmic silence is not that civilizations die. It is that they are hiding. This idea, known as the dark forest hypothesis, reframes the entire universe from a hopeful garden into a lethal hunting ground. Inspired by the science fiction of Liu Cixin, it offers a grim but logical solution to the Fermi paradox. The premise is stark. In a dark forest, every hunter knows that other hunters are present, but they cannot see each other. Any sound, any flicker of light could reveal their position to a predator. The only rational strategy is absolute silence, to move with stealth, and to shoot first at any sign of another. In this cosmic analogy, every star system is a hunter huddled in the underbrush, holding its breath. The logic chain that leads to this paranoia is cold and compelling. It begins with a few basic assumptions about the nature of life in the universe. First, survival is the primary need of any civilization. Second, civilizations will inevitably grow and consume resources, creating a fundamental competition for finite cosmic materials. And third, the distances between stars are so vast that communication is slow and trust is impossible to establish. You can never know the true intentions of a civilization hundreds of light years away. By the time their peaceful message arrives, their warships, launched in suspicion centuries earlier, might already be halfway to your star. Given this deadly uncertainty, the safest assumption is the worst one. Any other civilization you detect is a potential existential threat. The only way to guarantee your own survival is to eliminate them before they can do the same to you. In this universe, the great filter is not a technological bottleneck or a natural disaster. It is a behavioral imperative, a simple rule of cosmic Darwinism. Civilizations that are loud, that broadcast their presence with radio signals or build conspicuous megastructures, are the ones that get culled. They make an evolutionary mistake. The ones that survive are the quiet ones, the ones who listen intently but never speak, who cloak their emissions and mask their worlds. Their signature is not a beacon but a perfect simulated silence. This hypothesis transforms our search for extraterrestrial intelligence into a potentially suicidal act. Programs like SETI, which listen for signals, might be safe, though perhaps futile. But active SETI, the deliberate broadcasting of powerful messages towards other stars, could be seen as the equivalent of standing in that dark forest and shouting, "Here I am." Proponents of this view argue it is an act of profound naivete, risking the attention of a civilization that follows the dark forest logic to its grim conclusion. The silence we have taken as a puzzle is, in this scenario, the deafening sound of universal caution. It suggests a cosmos not of dead civilizations, but of living, paranoid ones, each alone in its own leafy hollow, finger on the trigger, praying not to be seen. This is a universe where the ultimate achievement is not to conquer the stars, but to become invisible to them. The ruins of great empires are scattered across our own planet, silent monuments to a truth we often forget. Civilizations, even the most powerful and sophisticated, are not permanent. They can and do collapse. By studying these historical breakdowns, we are not looking at ancient history alone. We are examining a series of controlled experiments in societal failure, each one a miniature, planetary-scale preview of the challenges that could form a great filter. The Roman Empire did not fall in a day. Its decline was a slow unraveling, a death by 1,000 cuts, economic strain from maintaining a vast military, a growing dependence on foreign resources, debasement of its currency, and deep social inequalities between the wealthy elite and the common people all created systemic fragility. Then external pressures arrived, migrations and conflicts at its borders. While a shifting climate may have impacted agricultural yields, the complex system, stressed from within and shocked from without, eventually fractured. Across the Atlantic, the classic Maya civilization faced a different but equally instructive collapse. In the heart of the Yucatan Peninsula, mighty city-states like Tikal and Palenque thrived for centuries, mastering astronomy, mathematics, and architecture. Theirs was a story of spectacular success until it wasn't. Researchers point to a combination of intense warfare between rival cities, severe, prolonged droughts linked to climate shifts, and perhaps most critically, the overexploitation of their environment. As populations grew, forests were cleared for agriculture, leading to soil erosion and reduced rainfall. The very land that sustained them could no longer support the societal complexity it had created. Even earlier, the interconnected civilizations of the late Bronze Age Mediterranean, from the Mycenaean Greeks to the Hittites and the Egyptians, experienced a synchronized collapse around 1200 BC. This was a true systemic failure where a network of trade, diplomacy, and cultural exchange disintegrated almost simultaneously. The causes were likely a perfect storm, what historians call a multi-causal collapse. Earthquakes and volcanic activity may have played a role, but so did the disruption of vital tin and copper trade routes, widespread conflict from marauding groups often called the Sea Peoples, and possibly regional climate instability affecting harvests. The interconnectedness that had been their strength became their vulnerability, as failure in one region cascaded catastrophically through the entire network. From these and other examples, clear, haunting patterns emerge. Resource depletion, whether it's the silver mines of Rome, the fertile soil of the Maya, or the tin trade routes of the Bronze Age, is a recurring theme. Climate change and environmental stress, often exacerbated by human activity, apply relentless pressure. Social stratification and inequality can erode cohesion, making collective action in a crisis nearly impossible. And a persistent failure to adapt, a rigid adherence to old ways in the face of new realities, seals the fate of societies that once seemed unshakable. These collapses were not existential for humanity as a whole, but they were absolutely existential for those specific cultures, their identities, and their dreams. They show us that progress is not a one-way street. Complexity carries a cost, and systems can reach a tipping point where they become too brittle to withstand the shocks that are inevitable over centuries. For a technological civilization dreaming of a million-year future, these historical case studies are the most relevant textbooks we possess. They are microcosms of the Great Filter, demonstrating that the greatest threats may not be alien invasions or rogue asteroids, but the slow, internal erosion of the foundations we take for granted. To endure for the long term, a civilization must learn to read these patterns in its own story, to see the warning signs of resource strain, environmental feedback, and social fracture, and to cultivate the flexibility to change course before the path leads over a cliff. Our past is a gallery of ghosts, each one holding a mirror to our potential future, asking us if we have learned to see what they could not. Perhaps the most intimate barrier is not found in the stars, but within ourselves. We are a species sculpted by a specific world, with minds and bodies fine-tuned for life on a planet of grasslands, forests, and tribal communities. This biological and psychological inheritance, the very essence of what makes us human, may be fundamentally mismatched for the demands of an interstellar future. The first limit is a deep, almost primal yearning for a place called home, Our sense of identity, our stories, our connection to ancestors and descendants are all rooted in a specific landscape. Can a civilization maintain its cultural and psychological coherence when home is a fragile metal cylinder hurtling through the void for generations, or a domed colony on a dead, red rock under an alien sky? The psychological strain of a generation ship presents a monumental challenge. Envision a community born, living, and dying within the same enclosed walls, knowing their only purpose is to maintain the ship so that their distant descendants might one day see a new sun. They would tend gardens they never planted for a shore they will never touch. The social dynamics in such an environment could fracture under the pressure of confined living, limited social pools, and the sheer weight of a mission whose payoff is hundreds of years away. Boredom, conflict over resources, or a simple loss of faith in the mission could unravel the entire endeavor from the inside. Even if a colony is successfully established on another world, new filters emerge over cosmic timescales. Isolated for centuries, the colonists would inevitably diverge culturally and biologically from Earth. Their language, customs, and even their physical adaptations to a lower gravity or different atmosphere would make them distinct. After 1,000 years, would they still see Earth as their motherland, or as a distant foreign power making claims on their new home? The history of human exploration on Earth is filled with colonies that eventually sought independence. This dynamic, projected onto an interstellar stage, suggests that expansion might not create a unified galactic civilization, but a scattered diaspora of increasingly alien cultures, potentially leading to misunderstanding or conflict over resources across the light years. This leads to the most introspective question of all, a filter of will. Do civilizations, once they achieve a comfortable, sustainable existence within their own solar system, simply lose the drive to venture further? Imagine a future where humanity has built beautiful orbital habitats, perfected virtual realities of infinite complexity, and solved the challenges of health and longevity. The urge to undertake a perilous, multi-generational pilgrimage to another star might fade, replaced by the allure of inner exploration. The frontier spirit that propelled us across oceans and into space may not be a permanent fixture of an advanced society. It could be a phase, an adolescent restlessness that matures into a desire to cultivate our own garden rather than constantly seek new ones. The silence we observe, then, might not be the silence of extinction. It could be the quiet hum of contentment, the sound of countless civilizations who looked into the void and decided, after careful consideration, that they preferred to stay home. They turned their genius inward, exploring the vast landscapes of consciousness, art, and simulated experience, finding fulfillment within their own celestial backyard. This introspective angle forces us to take our soft, internal barriers as seriously as the hard laws of physics. The ultimate challenge to becoming an interstellar species may not be whether we can build the ship, but whether we, as a collective psyche, still want to board it when the time comes. The ultimate source of power in any solar system is its star. To ascend beyond our planetary cradle, we would need to command energies that dwarf our entire global output today, perhaps even the complete luminous output of our Sun. This is the dream of a Kardashev Type II civilization, a society that can harness the total energy of its home star. The theoretical tool for this is a Dyson sphere, a vast swarm of orbiting collectors that would capture every photon of sunlight. Yet this grand vision may conceal the most practical of all filters, a simple, brutal law of thermodynamics. Energy is not free. Collecting it, managing it, and using it for interstellar travel comes with an unforgiving price tag that may be too high for any civilization to ever pay. The first cost is purely material. To build a structure or even a loose constellation of collectors that could encircle a star requires astronomical amounts of raw matter. Some proposals suggest dismantling entire planets like Mercury for their metal and rock. The scale of this engineering is almost incomprehensible, a project that would take centuries or millennia, requiring self-replicating machines and an unshakable societal commitment spanning generations. But even if the engineering were solved, the physics of waste heat presents an insurmountable barrier. Every machine, every computation, every use of energy eventually produces waste heat. On Earth, this heat dissipates into the atmosphere and out into space, but a Dyson sphere, by its very design, traps that energy within a closed system. If a civilization inside such a sphere tried to use even a fraction of the sun's colossal power for computation or industry, the interior would rapidly heat up to intolerable, sterilizing levels. The sphere itself would glow brightly in the infrared spectrum, a beacon of wasted energy. This is not a simple engineering problem to solve with better radiators. It is a fundamental thermodynamic limit. You cannot perfectly recycle energy, and the waste heat from using a star's power would cook any civilization that tried to contain it. This suggests a Type 2 civilization, as traditionally imagined, might be physically impossible. A more realistic approach might be a partial swarm, using only a percentage of the star's output to avoid overheating. But that still leaves the economic filter, perhaps the most daunting of all. Let us assume a civilization could build a partial swarm and manage the heat. They now have a staggering amount of energy at their disposal. The next logical step is to use that energy to propel starships to other systems. But here we confront the rocket equation, a tyrant of physics. To accelerate even a modest ship to a meaningful fraction of light speed requires propellant, and the faster you want to go, the more propellant you need. But that propellant itself has mass, which requires more energy to accelerate, in a vicious cycle that grows exponentially. To send a ship on an interstellar journey within a human lifetime might require energy equivalent to a significant portion of a star's output, focused on a single vehicle. The cost in terms of materials, energy, and time would be the project of an entire planetary civilization for centuries. Would any society, no matter how unified, make that sacrifice for a probe that might not send back data for 1,000 years? The economic and social will to undertake such a generational burden with no immediate return might be a filter that stops expansion in its tracks. This paints a picture of a universe where civilizations can rise, master their planets, even harness a portion of their star's energy, but then hit a firm ceiling. They become brilliant, sustainable islands, but islands nonetheless. They may build beautiful orbital cities and delve into virtual realities, but the dream of physically touching another star remains just that, a dream, forever out of reach, not because of a lack of imagination, but because of the cold, hard arithmetic of energy and economics. The silence we hear may be the quiet hum of 1,000,000 advanced homebodies, each tending their own stellar garden, having found that the price of a ticket to the next star is more than any universe could ever afford. Our antennas are not just listening devices, they are philosophical instruments pointed at the stars to ask the most profound questions about our place in the cosmos. This is the work of SETI, the search for extraterrestrial intelligence, a scientific endeavor that transforms the great filter from a theory into a testable hypothesis. For decades, projects like SETI have scanned the radio sky, sifting through cosmic static for a pattern, a signal, a whisper of another mind. The act of listening itself is a powerful statement. It assumes that if other civilizations exist, they might be communicative, at least for a time. It is a patient, passive form of exploration, gathering data without revealing our position. In this way, SETI is widely seen as the cautious, scientifically prudent path. It carries minimal risk while offering a potentially universe-altering reward. A single confirmed signal would answer the Fermi paradox in an instant. telling us we are not alone and that at least one other civilization passed whatever filters existed up to the point of building a transmitter. The silence it has found so far, while profound, is still data. It helps us refine our models of where and how to look, and it quietly amplifies the mystery of the great filter with every empty scan. But listening is only one side of the conversation. A much more controversial idea is METI, messaging to extraterrestrial intelligence. This is the active, deliberate broadcasting of powerful signals toward specific star systems, a cosmic hello. Proponents argue that someone has to make the first move. If every civilization is only listening, the universe will remain forever silent. They see METI as a bold step of cosmic optimism, an expression of our desire to connect and learn. A carefully crafted message could convey the essence of humanity, our mathematics, our biology, our art, reaching out to share the story of our world. This optimism, however, collides directly with the darkest interpretation of the filter. Critics of METI, including esteemed scientists and thinkers, warn that it could be an act of profound recklessness. Their argument is rooted in the logic of the dark forest hypothesis. In a universe where survival is the primary imperative and trust is impossible across light years, broadcasting your location is an existential risk. You cannot know the intentions of whoever might be listening. A civilization that detects your signal might not send a greeting. It might send a weapon or simply mark your star system as a future threat to be neutralized. From this perspective, METI is not bold. It is like standing in that dark forest and lighting a signal flare. It violates what could be a universal survival strategy, silence. The debate between SETI and METI is therefore not just a technical disagreement. It is a fundamental clash of cosmic philosophies. It forces us to choose between hope and fear, between a vision of the universe as a community and a vision of it as a battlefield. Our stance on whether to shout or stay quiet is the most direct policy reflection of which great filter scenario we find most compelling. If we believe the filter is behind us, and we are the rare, lucky ones, then METI seems like a noble attempt to find company in the void. But if we suspect the filter is ahead of us, particularly a filter of predation or competition, then METI appears as a potentially catastrophic mistake. This ethical dimension makes the search for intelligence uniquely charged. Every frequency we monitor, every message we contemplate sending, is a bet on the nature of reality itself. Are we casting a line into a friendly sea, or are we poking a stick into a dark cave? The protocols governing this activity are still being written by a patchwork of scientists and institutions because there is no global consensus. We are making up the rules for cosmic diplomacy as we go, with the stakes being nothing less than our entire future. This tension between our longing for contact and our instinct for self-preservation may be the final, intimate filter we must navigate, not with telescopes but with wisdom. The universe does not grade on a single subject. Its final exam is cumulative, covering every discipline from astrophysics to sociology. So perhaps the most honest answer to the silence is not a single, terrifying filter, but a complex mosaic of probability, where each challenge chips away at the number of civilizations that make it to the next round. We are not looking for one impossible wall, but navigating a labyrinth of increasingly difficult rooms, and the exit is nowhere in sight. This synthesized view accepts that many of the theories we have explored contain a piece of the truth. It is likely a little bit of everything. The rare Earth hypothesis suggests the starting line itself is sparsely populated. The cosmic shooting gallery of gamma-ray bursts randomly eliminates promising contenders over deep time. Then, for the lucky few that develop technology, the gauntlet truly begins the perilous adolescence of nuclear weapons and climate instability, the siren call of virtual reality, the economic and physical walls of interstellar travel. Each of these is a filter in its own right, a statistical reducer. A civilization might survive its planetary crises only to lack the collective will to journey to the stars. Another might master interstellar travel but fall prey to an ancient, lurking artificial intelligence. The survivors from one epoch become the contestants in the next, their numbers winnowed down with each successive challenge. This probabilistic maze is a more daunting but also more actionable picture than a single, mysterious barrier. It means our survival is not a binary pass or fail event, but a continuous project of risk management across multiple fronts. Our task, therefore, is not to find and defeat one mythical monster. It is to systematically strengthen our resilience against every known category of existential threat. We must fortify our planetary environment against climate change and biodiversity loss, building sustainable systems. We must develop rigorous international safeguards for emerging technologies like advanced artificial intelligence. We must foster global cooperation to prevent conflict and manage resources, and we must pursue spacefaring capability not as a distant dream, but as a strategic imperative to ensure our story is not bound to a single world. Each of these efforts increases our cumulative probability of success. By shoring up our defenses in sociology, technology, and planetary science, we are essentially studying for all the possible exams the universe might throw at us. We may never know which filter was the most lethal for others, but we can work to ensure that none of them prove lethal for us. This perspective transforms our cosmic anxiety into a clear, if immense, to-do list. The silence is not a verdict, but a set of instructions written in the negative space of all the voices that are no longer there. The silence we began with is not empty. It is full of meaning, echoing with the ghosts of possibilities we have traced together. From the improbable spark of life in a primordial ocean to the perilous adolescence of nuclear technology, from the cold equations of interstellar travel to the quiet threat of our own contentment, we have mapped a spectrum of barriers that could stop a civilization from ever reaching the stars. Each theory, whether a filter of destruction, limitation, or transcendence, offers a different lens on that profound cosmic quiet. Yet they all converge on a single, undeniable point of impact, the present moment, and the civilization currently holding its breath, us. This is the central, sobering gift of the Great Filter concept. Regardless of where the true barrier lies, whether in our miraculous past or our uncertain future, the framework places an immense and immediate responsibility squarely upon our generation. It transforms our global challenges from political or economic issues into a unified species-level project. The mandate is clear and urgent: to prioritize long-term survival over short-term gain, to cultivate global cooperation over ancient divisions, and to approach every powerful technology with a foundation of wisdom and ethical stewardship first. We are the first generation to see our planet from the outside, a pale blue dot in the void, and to understand the fragility that image represents. With that vision comes a duty. The choices we make in the coming decades about our climate, our alliances, and our inventions will write the next paragraph in a story that is either uniquely human or universally tragic. We may well be the universe's fledgling attempt to become aware of itself, to look back upon the cosmic dawn and ask, why? Our profound task is to ensure that this awareness does not end with us, that it learns, grows, and one day reaches out to touch the light of other suns. This is not a burden for distant leaders or future generations alone. It is a call that echoes for every one of us to support the science that illuminates our path, to champion the rational policies that safeguard our common home, and to think of ourselves not merely as citizens of a nation, but as stewards of a civilization standing at the most consequential crossroads it may ever know. The great silence awaits our reply.